Hello everyone, I am Sivaanandh Muneeswaran and I will be presenting our work Peekaboo, hide and seek with malware through lightweight multi-feature based linear hybrid approach. According to a report by Cisco, approximately 31% of organizations have encountered cyber attacks in 2019. Cybersecurity related threats almost cost 17.7 billion US dollars to organizations in Singapore. A major cyber attack demands for ransom from victims would cost around 193 billion US dollars and could affect more than 6 lakh businesses worldwide. Data breaches, malware attacks, hacking, vulnerabilities exploitation, etc. are the major threats in cybersecurity, out of which malware attacks account for a large percentage of the threats. Malware attacks could cause huge damage, such as catastrophic failure of an individual computer and network, and can cause hardware failure, data loss, and could also infiltrate corporate network. Malware is a primary choice of weapon to carry out malicious intents, and it is also the largest contributor to economic loss among all types of cybersecurity threats, according to a report by Accenture. McAfee has reported over 60 million new malwares just in the first quarter of 2019. Therefore, faster, more scalable, and accurate malware detection methods are needed. Although the detection accuracy of signature-based detection systems is high, with very few false positives, it requires malware specialists and extensive domain knowledge to develop the signatures. Moreover, signature-based detection methods cannot detect the new variants of malware from the existing ones through code of obfuscation, encryption, and polymorphism. It is also possible to scale up to thousands of new malware discovered every day. In order to understand the behavior of the malware, machine learning based models are employed, which uses less resources and the manpower needed is also reduced. Behavior based detection techniques use features that are more representative of malware behaviors, as malware variants have different code form but similar behavior and functionalities as those malware the variants originate from. Behavior-based approaches can capture unknown variants of existing malware and classify them into known malware classes. Most of the existing solutions are mostly behavior-based approaches. However, in most of the cases, only a single type of feature is used. In such approaches, less useful information is used, while all other features are completely discarded, and this leads to lower accuracy and higher false positive rate. Consider the other case of using multiple features. The selected features need to go through a feature engineering process to obtain high-level representation. Moreover, the selected features need to be combined through feature fusion. This feature engineering step is crucial to the performance, and it is extensively domain knowledge driven. Therefore, we move forward with lenient hybrid solutions, which are complex and challenging. Traditional hybrid analysis involve both static and dynamic analysis, which is quite common in the existing approaches. However, hybrid analysis is challenging as each sample has to undergo both static and dynamic analysis, and the runtime of dynamic analysis increases significantly. To address these issues with dynamic analysis, the usage of powerful host machines could be a potential solution, but it is not possible at industrial scale. Moreover, the runtime can be intentionally shortened to reduce the time resource overhead, but it leads to premature termination of analysis before the malware behaviors are captured. Static analysis is efficient since it does not require huge computational complexity. Therefore, how to create a lenient hybrid malware detection method which involves static and dynamic features which could also improve the performance. Thus, we propose to reduce computational overhead during dynamic analysis by performing dynamic analysis over a partial set of samples. The problem statement gives rise to the following research questions. How to integrate the information obtained from different sources for malware detection and classification. How to address the imbalanced feature extraction cost in hybrid analysis due to the inefficiency of dynamic analysis in practical scenarios without risking earlier termination of the dynamic analysis. How to make hybrid analysis more efficient for a large corpus of samples without needing to significantly increase the computational capacity. We propose a novel behavior-based model that uses lenient hybrid analysis. Our approach has two components. The first component is the data extraction, where the data for performing static and dynamic analysis is extracted. The second component is the partial feature integration, where partial multi-view learning method is used to integrate the features collected using both static and dynamic analysis. We use opcodes and API calls as the features, where API calls are high-level functionalities for any software to interact with system resources, and opcodes are the portion of a machine learning instruction that specifies the operation to be performed. Our approach could be seen as two models. One is the primary model, which is the opcode model, trained based on the static analysis of all the malware samples. And second is the secondary model, which is the API call model, which is trained based on dynamic analysis of the subset of malware samples, which acts as a secondary source of information. We propose a multi-feature extraction mechanism based on lenient hybrid analysis for a large corpus of benign and malicious samples, and this approach improves the performance. We propose a few-shot learning method for model training on API calls in malware detection and classification tasks. We also propose using a partial multi-view learning method, wherein a feature integration process that integrates the feature collected using both static and dynamic analysis into a single model for malware detection and classification. Then we develop models for binary classification into benign or malware classes and multi-class classification models to classify the malwares into different classes. From the entire corpus of malware samples, we select a subset of samples in which dynamic analysis is undergone in a virtual environment, thereby extracting API calls for the subset of data. The entire corpus then undergoes static analysis and we obtain the opcode dataset. These two steps constitute the data extraction part. In the partial feature integration component, the API call model and the opcode model transform the API call dataset and the opcode dataset into the numerical features respectively. Then these two features are integrated and a binary classifier and a multi-class classifier is trained over the integrated features. The lenient hybrid analysis can be treated as a speedy version of traditional hybrid analysis. In this case, we select a subset of samples from the entire corpus and we execute dynamic analysis only for the subset. However, the entire corpus undergoes static analysis. Static analysis can be treated as a primary information source, while the dynamic analysis can be treated as a secondary information resource to the primary model. Peekaboo integrates both static analysis and dynamic analysis for effective malware detection and classification. We have selected two features for our approach. The first one is API calls. API calls monitor the sequence of function calls the software makes to interact with the system resources and the flow of the program. It could be seen as high-level functionalities and can be used to understand the behavior of the malicious program. The next feature selected is opcode. It is the portion of a machine language instruction that specifies the operation to be performed. It also reveals significant statistical differences between malware and legitimate software. It serves as a basis for the detection of malicious executables. API calls are extracted dynamically by executing malware samples in a virtual environment. Opcodes are extracted by analyzing and disassembling the malware binaries. API calls are obtained only for a subset N through dynamic analysis, and the size of the subset is much smaller than the entire corpus, whereas opcodes are obtained for the entire corpus through static analysis. In partial feature integration step, we train two recurrent neural networks to transform the API calls and opcodes into numerical features and apply a partial multi-view learning method to integrate them into a single feature set, which could be then used to train a final machine learning model. Each data source is treated independently and converted into prediction scores to the recurrent neural network models. It could be seen that there is a whole block of API call data missing after the feature transformation step, and this blockwise missing data problem is transformed into missing value imputation problem. The two recurrent neural networks are trained independently using API call and opcode sequences. Hence, the last layer of the models would be a softmax layer. Therefore, the softmax layer outputs a prediction score. After training, we obtain two models, FA and FO, based on that API call dataset and the opcode dataset. We then construct the matrix P such that if the sample is in both dataset for DA, that is the dataset for API call, and DO, the dataset for opcode, then the prediction scores are obtained from the corresponding RNN models and concatenated. Otherwise, the prediction score from opcode model is concatenated with not a number in place of API call prediction score. So the resulting matrix P is a matrix with blockwise nans. In the future integration step, we use a missing value estimation algorithm. This algorithm is applied over the matrix P, thereby obtaining a complete future matrix with not a numbers replaced by numeric values as shown in the last block of the figure. We have used several popular missing value estimation algorithms like KNN impute, where the missing values are approximated by other values of the K training examples that are closest to it. And other algorithms like singular value decomposition and expectation and maximization algorithm are also used for comparison and benchmarking purposes. Since the size of the API call dataset DA is intentionally made small for more efficient dynamic analysis, we need to perform few-shot learning to ensure that the model trained over this dataset can generalize. The API call sequences can be considered as sequential data, and we use the modified version of EDA, that is the EC data augmentation approach, which is a data-centric few-shot learning approach. And the approach augments existing data by adding randomness based on synonym replacement, random insertion, random swap, and random deletion. Since synonym replacement and random insertion involve operations of synonyms of the words in the corpus, and we do not have or define such synonyms of API calls, we only use the remaining two methods, that is random swap and random deletion. This introduces more randomness so that the learning algorithm FA for the API calls is robust to overfitting. Considering the dataset, we use the API-MDS dataset, which is publicly available for the API call sequence. The opcode sequence dataset is obtained by disassembling the software binaries through the Python plugin R2Pipe. In total, we gathered 34,000 winning and malicious samples. Among all the samples collected, over 80% were collected after the late 2019. Among 34,000 samples, we randomly selected 4,500 samples for more efficient dynamic analysis based on our computational capacity. We then split the entire dataset into training. 80% constitute for training, 10% constitutes the validation test, and the 10% constitutes the test set. These are examples of API call dataset and opcode dataset. The table on the left shows the distribution of Peng and malware classes. The Peng software receives a single label as Peng. The malware receives the label malicious and an additional label of the malware class. We do not use any detection labels provided by antivirus vendors, since different vendors have their own way of labeling malware classes. To consistently assign labels for the malware, we use a state-of-the-art malware labeling tool called AV Class 2. We have 8 different malware classes like worm, downloaded, greyware, virus, backdoor, ransomware, rogueware, and spyware. In addition, the final module was also evaluated on a small set of malware samples that are of previously unseen malware classes. These samples come from malware classes the multi-class classifier has not seen, so it will not classify them correctly. We only evaluated this set of samples from unseen malware classes in binary classification setting. This unseen malware class dataset consists of only 179 malicious malware samples. We conduct experiments for both binary classification and multi-class classification. The first layer of RNN is the embedding layer, followed by a one-dimensional convolutional layer with ReLU activation. Next, a one-dimensional max pooling layer is used to reduce the size of the network. The LSTM and GRU layers are then employed and followed by a fully connected layer which flattens the output. The final output layer is a fully connected layer with softmax activation. In addition, dropout and regularization are applied to reduce overfitting. The sequences of API calls and opcodes are treated as sequences of text. In our setting, each API call or opcode will be naturally regarded as a token. The individual API call model can be seen as an assistant of the opcode model. Hence, we could expect the final model to perform at least as well as the opcode model. Given this intuition, we use the performance of the opcode model as the baseline. We transform the features, opcodes, and the API calls after few-shot learning and then integrate the features. The figure shows the test accuracy of both binary and multi-class API call models with and without few-shot learning. The API call model without few-shot learning under multi-class setting can only achieve an accuracy slightly above 50%. Few-shot learning can improve the accuracy by almost 30% for the API call model in this case. The next table shows the performance of API call model, opcode model, and the final model with the best performance for both binary and multi-class classifications. The API call model can do very well for binary classification. However, the API call model only has an 80% accuracy for multi-class classification. This is expected because the subset is relatively small and it is difficult for a model trained on such small dataset to do well in this case. The opcode model achieves 98.5% accuracy for binary classification, but with a high false positive rate of 1.56%. In the multi-class classification task, the opcode model performs much better than the API call model with 90.8% accuracy, but it still has a high false positive rate of 2.34%. The false positive rate can be lowered after the future integration, thereby bringing the false positive rate to 0.45% in case of binary setting and the same in case of multi-class setting. All models can perform well at binary classification regardless of the feature set. In this table, we have plotted the results of the future integration algorithms along with the final classifiers, machine learning classifiers. For the multi-class classification, Arabos performs very poorly with extremely lower accuracy and a high false positive rate. The rest of the machine learning models perform quite well, achieving an overall accuracy of around 95% with a low false positive rate. We select two of them as our final models. For the binary classification setting, the EM algorithm for feature integration and KNN for classification is chosen as the best model. And for multi-class classification setting, we select KNN impute for feature integration and SVM with RBF kernel for classification as the best model. We have compared other recently related works that uses API calls, opcode sequences, or both as features for malware detection for the performance comparison. The evaluation metrics are accuracy, precision, recall, and F1 score. Peekaboo outperforms other state-of-the-art in all the evaluation metrics by relatively a huge margin. This figure shows scatter plots of the integrated features for the unseen malware classes. X2 is the feature that has missing values, that is the API calls, and X1 is the opcode feature. We use the trained opcode model as the baseline for detecting and for the small set of malware samples. The trained opcode model can only detect 96.09%, giving a false negative rate of 3.91%. We could see that some data points have relatively small values for feature X1 since the individual opcode model classified them incorrectly. By contrast, The feature X2 is large for all data points, meaning the individually trained API call model performs well to correctly transform the features into prediction scores, and more importantly, the expectation maximization algorithm can correctly assign the values for those samples that are missing API call sequences. The final model, that is the trained KNN classifier, can correctly detect all the malware samples using the feature set integrated by the EM algorithm. To conclude, we presented a multiple feature-based lenient hybrid approach for malware detection and classification. We utilized only a small portion of samples for dynamic analysis, reducing the computational burden. We also improved the accuracy and false positive rate through the feature integration and the data imputation algorithm. Our feature works include using more than two features apart from API calls and opcode, and also considering unpacking of the code. Thank you for listening.